Hello, my name is Shan. I would like to introduce our recent work designing haptic feedback for sequential gestural inputs. More specifically, in this work, we investigate a novel user interaction modality that uses mid-air hand gestures as inputs and provides haptic signals as the feedback. The input format of mid-air free hand gestures was focused because this type of input affords much more flexible and intuitive interactions compared with traditional surface inputs or handheld device inputs. It has been widely adopted across a broad range of applications, such as virtual 3D operation in mixed reality and the remote commanding of smart home devices or in-vehicle systems. It also well supports the interaction with wearable devices, especially when the user is on the move, and it allows intuitive control that mirrors real-world physical interactions instead of solely relying on buttons. For such gestural inputs, haptic feedback delivered by wristbands were explored in this work as the primary feedback format. The haptic feedback was chosen considering that visual and audio feedback might not always be available, especially for wearable devices. It is also less distracting for tasks such as that are information-rich, such as driving or gaming. Furthermore, haptic feedback also aligns well with hand-related interactions, representing the tactile sensation we experience every day when interacting with physical objects. Among different types of haptic feedback, vibro-tactile feedback would be the most commonly used one. This is because vibro-tactors are lightweight to be integrated into wearable devices, and they're capable of conveying a wide variety of meanings by modulating vibration parameters, such as language representation, expressing metaphor-based meanings, or conveying social emotional messages. In this work, gestural inputs are designed to send shortcut commands, such as taking a picture or asking for information. After the gesture is made, corresponding vibro-tactile feedback is provided, allowing users to confirm that the system has received the command. More specifically, our study sequences multiple gestures together to increase the communication bandwidth, while distinct haptic patterns are provided for users to confirm each of the commands. An example of sequential gestural inputs would be taking a picture of a poster, sharing this picture with friends, and then setting a reminder for this event based on the date and other information on the poster. To investigate the communication performance for such sequential gesture haptic interaction, we structured the study into 3 steps. The very first step was to select appropriate shortcut actions with hand gestures and designing easily recognizable haptic patterns for those gestures. Next, we designed the first experiment based on single gesture interaction to determine the minimum duration of haptic patterns that balance the recognition accuracy and the communication efficiency. Following this, the second experiment was designed to examine sequential gesture interactions replicating real use case scenarios while considering multiple parameters simultaneously. In the first step of designing haptic patterns, 9 shortcut actions and their hand gestures were selected based on prior publications on gestural control and the discussion with UX experts. For each shortcut action, an intuitive haptic pattern was designed leveraging metaphor. For example, the haptic feedback for confirm consisted of 2 pulses, short and long, representing the check mark, and haptic feedback for setting a reminder was designed to mimic the tick-tock sound of the alarm clock. Given that we have 4 vibro-tactors on the wristband, motion effects were also utilized in haptic design, such as rendering the tactile sensation of moving toward oneself for the action of saving, and the motion effect of moving away from oneself for sharing. With these 9 pairs of hand gestures and haptic patterns designed, the first experiment was conducted to examine 4 pattern durations ranging from 0.1 second to 0.8 second. 3 experimental phases were designed for the task of matching the haptic patterns to the shortcut actions or gestures. The first phase was self-paced exploration, which allowed participants to explore the haptic pattern associated with each shortcut action, along with its hand gesture and haptic metaphor as many times as they desired. The second phase was the learning phase, where 9 haptic patterns were randomly sent, and the participants were asked to select corresponding shortcut action from the 9 options. Feedback was provided indicating whether the response was correct or not. If not, the correct answer would be provided to enhance the memory. The last phase was the testing phase, during which haptic patterns either correct or incorrect were triggered by the participant's hand gestures, and they were asked whether the received haptic pattern was the correct one for this hand gesture or not. Recognition accuracies were recorded from both learning and testing phases, which exhibit a similar trend along the pattern duration, where the accuracies began to plateau around 0.5 seconds. Particularly in the testing phase, accuracy as high as 92% was achieved at 0.8 seconds, which validates the effectiveness of our haptic design. When decreasing the pattern duration to 0.3 and 0.5 seconds, 80 to 90 accuracy could still be achieved. And even when pushing the duration to as short as 0.1 second, the recognition accuracy remains significantly higher than the chance level. Based on the results of the first experiment, pattern duration of 0.3 and 0.5 seconds were adopted for the next experiment of sequential gestural interaction. 6 out of 9 gesture haptic pairs were selected to form gesture sequences. Here, 4 independent variables were examined, including pattern duration, age of the participants, feedback strategies, and the number of gestures in the sequence. The 2 evaluation metrics were selected as recognition accuracy and the overall interaction time for the sequence. 5 experimental phases were designed here. The first 3 phases replicated those of the first experiment, while the last 2 introduced sequential gesture testing phases for the immediate and concatenating feedback strategies. The immediate feedback strategy means that the haptic pattern was provided immediately after each hand gesture. In contrast, for the concatenating feedback strategy, all haptic patterns were provided after all hand gestures are completed. In some trials, 1 incorrect haptic pattern was provided within the sequence. Participants were asked to identify whether all patterns are correct, and if not, to specify which one was the incorrect one. For the 2 feedback strategies, we hypothesized that the immediate feedback strategy would be easier for participants to adapt to, while the concatenating feedback strategy would enable faster and smoother interaction, since it allows users to perform the whole sequence of gesture rapidly without being interrupted or waiting for the haptic patterns to end. Given that we are examining both within and between subject variables, the linear mixed effects model was employed for significant tests with participants being the random effects. We first explored the variables of feedback strategy and pattern duration. The left plot of recognition accuracy shows that the pattern duration of 0.5 seconds depicted in darker blue led to significantly higher accuracy compared with the duration of 0.3 seconds. From the plot on the right, we can find that significantly shorter interaction time was used for the immediate feedback strategy as opposed to the concatenating feedback strategy. This analysis provides us with a general recommendation for these 2 parameters, where 0.5 second pattern duration and immediate feedback strategy could be beneficial to enhance the interaction accuracy and efficiency, respectively. We next investigated further the influence of the number of gestures, where we split the connected evaluation metrics for the feedback strategy pair into 3 numbers of gestures for the 0.3 and the 0.5 pattern duration separately. However, we found no significant differences across the 3 numbers of gestures for all 4 conditions tested. It suggests that the number of gestures in the sequence would not impact communication performance. Meanwhile, it is important to note that the memory loads associated with shortcut actions and hand gestures were intentionally not included in our experimental design, which might have an effect in real applications. The next parameter we examined was the age of the participants. Results show that across the 3 testing phases, the recognition accuracy significantly dropped along with the increasing age for the 0.3 second pattern duration, while no decreases were observed for the 0.5 second pattern duration. Such results indicate that haptic patterns with 0.3 second duration will be challenging for the older group of participants to differentiate. Given that age would have significant impact, we then arranged our final haptic design recommendations based on age groups. As illustrated in this plot, the top left corner represents the best performance with higher accuracy and shorter interaction time. It can be observed that for the younger participants represented in gray, the combination of 0.3 second pattern duration and immediate feedback strategy would be recommended. Because while all 4 combinations led to similar recognition accuracies, this specific combination achieved the shortest interaction time. For the older participant represented in pink, the combination of 0.5 second pattern duration and immediate feedback strategy would be recommended when considering both evaluation metrics. In addition to this final set of haptic design recommendation, another interesting point is that immediate feedback strategy always led to shorter interaction time in a reliable and significant way. Therefore, we further broke down the interaction time for the two strategies for detailed comparison. Firstly, with the concatenating feedback strategy, we found that the average duration for participants to switch between gestures was around 1.3 seconds. Then for the immediate feedback strategy, light green blocks represent the duration between gestures when the Carine haptic pattern was correct, and the darker green block represents the duration when the pattern was incorrect. From this, we derived that time needed to confirm a correct haptic pattern was roughly 0.3 seconds. In comparison, confirming an incorrect pattern needed around 1 second. However, with concatenating feedback strategy, participants actually lost such flexibility to move faster when detecting correct patterns, because a constant time gap was set before each haptic pattern. This gap contributed a lot to the longer interaction time for the concatenating feedback strategy, yet it was determined through a pilot study and was reported to be relatively short during experiment. Moreover, immediate feedback strategy also enabled shorter final response time, likely because the decision have already been made after each gesture. This shorter response time of the immediate feedback strategy, together with the difference between the confirmation time for the correct and incorrect haptic patterns, were both tested to be statistically significant, especially the longer confirmation time for incorrect haptic patterns, which also offers insights for new functionalities, where this system could predict the user behavior based on the prolonged time. Overall, to conclude, I would like to highlight again the three contributions of this work. First, we designed the metaphor-based haptic patterns rendered by wristband to provide effective feedback for gesture-delivered shortcut commands. Then, we identified the trade-off between recognition accuracy and haptic pattern duration when expressing semantic information using full web detectors. Finally, we provide empirical haptic design recommendations for sequential gesture interaction for both younger and older users, while detailed comparisons of the interaction time were also provided for the two feedback strategies of sequential gestural inputs. Thank you.